When you think about what makes a material strong or colorful or magnetic, what comes to mind? Probably perfection, right? We picture atoms all lined up in this perfect, flawless grid. But today, we're going to see that the real magic, the secret life of solids, is actually all about the mistakes.
I mean, this is the picture we all learn in school. It's beautiful, it's ordered, it's totally predictable. In this perfect world, every single atom is exactly where it's supposed to be, creating this perfect pattern that just goes on and on. It's clean, it's simple, and, well, it's not the whole story.
Because here's the secret. In the real world, that perfect lattice just doesn't exist. And it turns out, that's a very good thing. The most interesting, the most powerful properties of the materials that build our entire world, they don't come from perfection. Nope, they come from the flaws, the defects, the tiny little imperfections that break the pattern.
So, let's open up the catalog and get to know some of these game-changing flaws. We're going to start with what are called point defects. These are tiny disruptions happening at the level of just a single atom. They're so small, they don't even change the material's basic chemical formula.
First up, we've got the Schottky defect. Okay, think of it like this. You're in a packed movie theater, and every single seat is supposed to be filled. A Schottky defect is like one guy and one girl getting up and leaving together. You're left with two empty seats, but the overall balance of the audience is pretty much the same. An equal number of positive and negative ions just go missing, which keeps the whole crystal electrically neutral.
All right, now let's meet the Frankel defect. Back to our movie theater. This is like a smaller person leaving their assigned seat and deciding to just go stand in an empty aisle. They're still in the theater, right? They just aren't where they're supposed to be. A smaller positive ion literally hops out of its spot and squeezes into a space where no ion should be.
So let's put them side by side. With a Schottky defect, atoms physically leave the crystal, so pretty logically, the overall density goes down. But with a Frankel defect, the atom just moves around inside, so the density stays exactly the same. And this kind of tells us when these are likely to happen. Schottky defects are common when the ions are about the same size, like in table salt. Frankel defects, they happen when one ion is way smaller than the other.
So now that we've got the basics down, let's see where this gets really interesting. What happens when a flaw actually changes the chemical recipe of the material itself? This is the point where imperfections stop being simple mistakes and start creating entirely new functions. And this brings us to a new class of defects that actually mess with the chemical recipe. They're called non-stoichiometric defects. I know, it's a mouthful, but it's just a fancy way of saying the ratio of positive to negative ions is no longer that perfect, neat little ratio. One way this happens was with a metal excess defect, where you end up with more metal ions than you're supposed to have.
And this process explains something we can actually see with our own eyes. Take regular table salt. It's clear, right? Well, if you heat it in sodium vapor, a negative chloride ion pops out, leaving a hole. An electron then rushes in to fill that empty spot. This trapped electron is called an F-center, and it totally changes how the crystal interacts with light. It absorbs certain wavelengths, and bam, the salt crystal looks yellow. A simple flaw literally creates color out of nowhere.
And believe me, these defects aren't just rare little accidents. Just look at this number for vanadium monoxide, a staggering 14%. 14% of its atomic sites are just empty. This isn't some tiny error, it's a fundamental feature of the material, and it makes its actual density way lower than what you'd calculate if you assumed it was a perfect crystal.
Now, it's not always about having too much metal. The exact opposite can happen too, leading to what we call a metal deficiency defect. This is really common in materials where the metal can have different electrical states, and it leads to some pretty clever chemical gymnastics.
Iron oxide, rust, is the perfect example. Some of the positive iron ions are just gone. So to keep everything electrically balanced, a few of the remaining iron ions just give up an extra electron, changing from a +2 charge to a +3 charge. And the result? The formula isn't a perfect FeO. It's always missing a little bit of iron. The material is literally defined by what's not there.
Which brings us to a massive idea in all of modern technology, doping. Okay, so we've seen how defects can happen naturally, but what if we could create them on purpose? Well, that's exactly what doping is. We intentionally sneak impurities into a pure crystal to create specific, controlled flaws. And why? Because those flaws give us the semiconductors that run absolutely everything, from your laptop to your smartphone. Our entire digital world is built on engineered imperfection.
So let's shift our focus to another kind of engineered imperfection, but this time we're going down to the electronic level.
The magnetic properties of materials, they don't really come from where atoms are placed. They come from the behavior of their electrons, specifically whether those electrons are all neatly paired up or if they're flying solo.
First, you have diamagnetic materials. In these substances, every single electron has a partner. They're all perfectly paired up, spinning in opposite directions. You can think of it as electronic perfection. And what's the result? Well, they're ever so slightly repelled by a magnetic field.
The key here is those paired electrons. It means there are no tiny internal magnets or dipoles to speak of. So when you bring a magnet close, they get weakly pushed away. This is basically the default magnetic behavior for materials that don't have any electronic flaws. But, things get way more interesting when you have unpaired electrons. These materials are called paramagnetic, and here that electronic perfection is broken. You've got these solo electrons, and each one of them acts like a tiny microscopic magnet.
So, unlike their diamagnetic cousins who get pushed away, these materials are weakly attracted to a magnetic field. All those tiny internal magnets try to line up with the external field. It's not a strong pull, but it's a definite attraction, all thanks to those wonderfully imperfect, unpaired electrons. And now for the superstar of magnetism, ferromagnetism. This takes that idea of unpaired electrons and just cranks it up to 11. In these materials, it's not just that unpaired electrons exist, it's that they learn to work together. They team up by the millions and millions to align their tiny magnetic fields into these big regions called domains.
This collective alignment, this amazing teamwork, is what makes materials like iron and nickel so special. It's the difference between a weak little attraction and that strong pull you can actually feel. And even better, it's why they can become permanent magnets themselves. All of that power comes from organizing the chaos of unpaired electrons into these cooperative groups.
So after looking at everything from empty spots in a crystal to unpaired electrons, we arrive at this really powerful conclusion. In the world of materials, flaws are not failures. An empty space, a trapped electron, an unpaired spin, these aren't mistakes we need to eliminate. They are features. They are the very source of the properties we depend on, from the color of a gem to the memory in our computers.
We've actually learned to see the power in the imperfections of matter, and we engineer them to build our world. So it makes you wonder, right? What if we applied that same thinking somewhere else? If the tiniest flaws can be the source of the greatest strengths, what could we possibly unlock by looking for the hidden features in other things we might mistakenly just label as imperfect?